Okay, welcome back. So we are now going to go ahead and continue our discussion of chemical reactions, and we're down to the last type of chemical reaction that we're going to be dealing with, and it's actually a very important one. As it turns out, this is such an important reaction that it actually encompasses some of the other kinds of reactions that we've already talked about, so that you can kind of see the interconnection later on. So this is now the oxidation reduction process. Okay, so let's take a look at what this particular reaction entails. And of course, if you have to always say oxidation reduction, well, that takes quite a hot mouthful. So sometimes this is referred to as the redox reaction. Not redox, but redox reaction. Okay, reduction, oxidation reaction. You might say, well, wait a minute, oxidation comes first before the reduction, so why not just call this oxred, for example? Well, I don't know, you're going to have to ask a true chemist about that particular reasoning. But this is now known as a redox reaction. And as it turns out, we've actually seen reaction like this before, but we've kind of given them slightly different names. One classic example of an oxidation reduction reaction, of course, it involves the formation of ionic compounds. When a metal combines with a non-metal, for example, okay, it is in the process of creating an oxidation reduction reaction. And the way we can kind of view of it is that we talked about the idea of mechanisms that drives chemical reactions. Okay, we talked about the idea of the formation of a solid, like in a precipitation reaction. We talked about the formation of gases, for example, like weak electrolyte and the gas formation from the breakdown of carbonic acid in water, for example. We also talked about the fact that you can have a production in such a way that you can have the production of water, like in an acid and base reaction, for example. The last driving mechanism that we haven't really covered is the idea of a transfer of electron. The electron actually gets transferred from one place to another. So we want to kind of take a look at that in a little bit more detail. Okay? Transfer of electron from one place to another. And as it turns out, that can be used as a way to kind of describe what's going on in an oxidation reduction process. And in so doing, we now go ahead and define two different situations, two different processes, so to speak. The first process is the process of oxidation. Okay? So what is it that we're talking about oxidation? When the process of oxidation, basically you're looking at a situation where something is giving up electrons. Okay? And in most cases, of course, it's going to be some sort of metal, for example. So the metal, for example, can start off as a neutral atom. And what happens is that during the process of oxidation, the metal then becomes a positive cation plus a certain number of electrons that are now loose. So in the case of sodium, for example, it would then become a +1 ion with 1 electron loose. If you look at magnesium, for example, then it becomes magnesium +2, and you have 2 electrons that are now available, and so on and so forth. So this is the process where you have oxidation, and usually the M is here is going to be representing a metal, something that loses an electron. And so you think about this, electron, lost. Okay, so there's a loss of electron in the process. Now, of course, there's a complementary process. Once the electron gets lost from the metal, where does it go? As it turns out, you now have a process called reduction. And this process is now kind of like a complementary process where instead of losing electron now, you're now going to gain electron. Okay? So something along the line will actually grab hold of the electron that came off of the metal itself. In this case, you usually will have some sort of a non-metal. Okay, of course, there's exceptional cases, but in general, this is now going to grab onto an n number of electrons. So it could be 1, 2, 3, however many. And in doing so, it now becomes a negative anion, with a charge equal to the number of electrons that it has captured, so to speak. So during the reduction process, we see that the electrons are actually gained by something. And usually, this something is going to be a non-metal. Not always the case, but non-metals are the prime suspects, so to speak. And in this process, we can also talk about the causes of oxidation and reduction, for example. In the case of a metal, for example, if the metal is sitting over here, why does it want to give up the electron in the first place? Something that's going to coax it to give up that electron. Something has to come along and say, hey, give me your electron. It kind of hijacks the electron from them. So that hijacker really is what we would call an oxidizing agent. So something that causes oxidation to occur, is going to be the cause for the oxidation. And guess what? Those are basically the substances that are going to grab hold of the electron and gain the electron in the first place. So interesting enough, if I have a non-metal over here, if the non-metal undergoes reduction, then because of this ability to grab hold of the electron, they are going to be the one that is going to be taking the electron away from the metals themselves. So in this process, we say that the object that is undergoing reduction are now the oxidizing agent. Okay? So the substance that undergoes reduction is now the oxidizing agent. Okay? At the beginning, it seemed kind of confusing, but if you kind of let your brain wrap around it for a little bit and think about it a little bit, it's not that difficult to understand, because in this case, there's actually two interacting partners. One, okay, is the one that is actually grabbing the electron from the other, and in doing so, it is the oxidizing agent is causing the oxidation to occur in the metal, and in doing so, having grabbed the electron, they are now undergoing the reduction process. They're reducing the process. In the same way, with the metal, they are the ones that are now able to deliver the electrons to the nonmetals over here. We call that the reducing agent. So the reducing agent is, of course, the substance that is responsible for reducing something. In order for them to reduce something, they have to be able to give up the electron to them and allow them to undergo the process of reduction. And this is kind of a strange thing. Whenever you see this term reduction, you think, well, I'm losing something, you're reducing. As it turns out, it has to do with the fact that, again, you're looking at negative charges that are being grabbed onto. So it looks like you end up with a negative sign over here, okay? So I believe that's the reason why they actually have that. There could be another reason that maybe chemists can better explain to you. But the idea is that you can always remember, okay, that when you undergo reduction, you're actually gaining something. You're gaining a negative object. You're gaining negative electrons. So that's the process over here. And so a lot of the things that we've already talked about, okay, in terms of ionic reactions, fall under this particular category, and we can actually see it pretty easily. So for example, if we look at some examples of this process, let's say I have magnesium solid over here, okay, and this is going to undergo some sort of reaction with oxygen gas, for example. So we know, for example, when this actually happens, I'm going to end up with magnesium, oxide, and this is going to be a solid. And if you look at balancing, this is going to be 2 here, 3 here, and now you have actually looked at a situation where you have a balanced chemical reaction equation. And this is now an oxidation reduction process, because in this case, what's happening is that the magnesium is actually giving up electrons. So in this case, you can think of the magnesium starting off as a solid, and then the oxygen sitting over here, say I have 1 to 1 at this point. Then what happens is that electrons will then migrate from the magnesium over to the oxygen. Okay? And in doing so, what you'll find is that when that happens, then the magnesium becomes a +2 charge. This is the case where now the magnesium becomes a +2 charge with those 2 electrons. That's the oxidation process. Okay, oh, hold on. I lost my pen cap over there. All right, sorry about that. So in this case, when that transfers over, now you can see the oxygen grabbing the 2 electrons now becomes a -2 process. So we say that in this case, the magnesium is undergoing oxidation and the oxygen is undergoing reduction. Okay? And because the oxygen is the one that actually stole the electrons from the magnesium in the first place, we say that the oxygen is the oxidizing agent. And of course, because the magnesium is able to give up the electron to cause the reduction of the oxygen, these are, of course, now the reducing agent. Okay? So again, after a while, you have to kind of get used to it. And they are going to be oxidized. Whatever is being oxidized is going to be the reducing agent. Whatever is being reduced is now the oxidizing agent, and vice versa. And this should not be too difficult because we've actually seen this before. Okay? However, sometimes you see oxidation reduction processes that are not so obvious, and it takes a little bit more kind of close scrutiny to be able to actually see what's going on. So let me just kind of show you how we can actually keep track of some of these more visually. In the textbook, they actually go through a process of calculating something called the oxidation number. Okay, for our purpose, we're not going to worry about that too much. If you go into a higher level course like this, chemistry 161, 162, for example, then oxidation number becomes very important in terms of keeping track of oxidation reduction reactions. For us, we're just going to look at it more qualitatively, and then if you are interested, the book does discuss oxidation number, and you can go ahead and research that on your own as well. But let's take a look at another way of looking at oxidation reduction and see if we can see some sort of visual clue as to what's going on aside from this definition here. The reason for this being difficult to see is sometimes it's kind of hard to see the migrations of electrons, especially if you have two metals that are interacting or two non-metals that are interacting. So it's much harder to kind of talk about balancing charges and see where charges are going to go. So in this case, we can now go ahead and come up with a different way of looking at it. So in terms of oxidation, how do we know when oxidation is occurring as compared to reduction? Okay, so let's compare the two side by side and see if we can kind of come up with some sort of idea. The whole idea is that when oxidation and reduction occur, basically you're going to end up with something that would end up with some sort of ionic state. So you're going to have either positive cation as a result or some sort of negative anion as a result of either losing or gaining an electron. So in terms of ionic state, this is going to be the positive ionic state. This is usually a negative ionic state, as in general, okay? But there's other ways of looking at it too. You can think in terms of electron transfers, for example. So if I think about electron transfers, if I look at oxidation reduction, for example, in this case, this is the case where, something loses an electron. So when it loses an electron, it usually becomes a positive, ion. So that means on this side, that means that this is going to be due to something that what? Gains electrons, Gains electrons. So what's going on in this case is that the transfer electron goes from this to that side. So the electron transfers over from whatever is being oxidized, undergoing oxidation, to the side that is now being reduced, reduction. So gain the electron going one way. Sometimes, as you said before, it might be kind of difficult to kind of keep track of the actual electrons that are moving. So what if we look at something else? Well, as it turns out, two substances or two elements that are really, really highly involved in this process of oxidation reduction we see over and over again are actually going to be oxygen and hydrogen. So if you can somehow keep track of these two elements, maybe they'll give us a hint as to what's going on. So in general, for example, in the case of oxidation, what you find is that this is a situation where you lose hydrogen. If you lose hydrogen from a particular substance, it's pretty obvious that in that case, there's a good chance that it's being oxidized. And on the other side, of course, if this stuff loses hydrogen, this guy's going to now gain hydrogen. And so in this case, the process of movement is now hydrogen goes from the side that is being oxidized to the side that is being reduced. And we'll see examples of this a little bit later on in terms of how to keep track of this. The last thing we take a look at is, again, the idea of now oxygen being transferred from one place to another. In the case of oxidation, as it turns out, what you find is that instead of losing something, electrons or hydrogen, now you're going to actually gain oxygen. So when something gains oxygen as a result of a chemical reaction, there's a good chance that it is undergoing oxidation at that point. Of course, in that case, that means that whatever is going to be gaining the electron, where is it gaining it from? It's gaining from the substance that is being reduced. So this actually now loses oxygen on that side. So notice in this case that the flow of the sun is now in the opposite direction. Oxygen actually flows from the reduction to the oxidation side. All right, so let's see what we mean by these different processes. So let's take a look at one where you can actually see and trace the idea of electron movement. Let's say I have a copper +2 ion over here, and let's say somehow it is finding itself near the vicinity of a zinc atom in this case. Well, interesting enough, what can happen is that this can actually interact and basically undergo an oxidation reduction process. So in this case, you can actually end up now with a zinc +2 and a copper neutral atom. That's interesting. Well, in this case, you actually see that, well, there must be some sort of transfer of electron along the way here. So initially, this guy had a +2 charge. That means it's missing 2 electrons. This guy's perfectly neutral. So it's got all its electrons. But notice what happened at the end. At the end, the zinc now has a +2 charge. That means it has what? Lost 2 electrons. So if that's the case, you can say, okay, if there's a transfer of electron now, 2 electrons from here to here, we can now trace the electrons. The thing that loses electron, well, here it is. The zinc is losing electron. That means this is now undergoing the oxidation process. The oxidation process. On the other hand, the copper is now receiving the 2 electrons. It gains the electron. This is undergoing the reduction process. So here's your oxidation reduction process. In this process. And so you say, well, why would that happen? What is going on in that situation? Well, imagine the following. Let's say if I have a solution, of copper nitrate. So imagine if I have this is now going to be copper 2 nitrate, so NO3 2AQ, okay, and it's in a solution. And as it turns out, when you dissolve copper nitrate in water, it actually turns kind of like a bluish color, okay? And the bluish color actually comes from the presence of the copper +2 ion sitting in there. And you find that in nature, a lot of minerals that have blue and green colors tend to have copper in them, the different ions of copper, +1 and +2. And so in this case, imagine now I also add into here, okay, some material, let's say solid aluminum. What will happen in this case? Well, interesting enough, this cannot undergo a reaction. It can actually undergo an oxidation reduction reaction, so that at the end you will actually end up now with aluminum nitrate. Okay, it's going to be AQ plus you end up with solid copper. Okay, from there. Interesting enough, what this allows you to do, it allows you to recover the copper that is in this aqueous solution. You're somehow able to kind of change a compound that contains copper into pure copper. You're not able to bring that copper out in that process. And so let's see what happens in this case. Okay? If you look at this, what you're looking at really is the interaction between aluminum and the copper, kind of like what's happening up here. So let's see what that looks like in this situation. In this case, this is a copper 2, so you have copper +2, and then of course you have your aluminum sitting over here. Okay? That's a solid material, okay? Neutral at this point. And as it turns out, by the time you get to here now, because the aluminum is able to combine with 3 of your nitrates over here, that means this is now a cation. So that means you ended up on this side with the aluminum +3 over here. And then of course here copper is sitting by itself. You now have your element of copper. In order for this to happen, something must happen in between these two on the reaction side. So let's see what happened there. Well, again, if you think in terms of a transfer of electron, this is the guy that initially was missing 2 electrons, and this guy had all of his electrons. And so what will happen is that you're now going to transfer the electrons over to over here. Okay? The problem, of course, at this point doesn't balance out properly. Okay? You have a +3 here, a +2 here, so I need to kind of balance out things. Okay? So for example, since aluminum is willing to give up 3 electrons to become a +3 charge, okay, I want to be able to receive 3 electrons. Here, this is only going to receive 2. So the idea is that I'm going to need a 3 in front of here and a 2 in front of here, so that I transfer a total of 6 electrons over. So that means 2 of the aluminum, each giving up 3 electrons, will give up 6 electrons. Then each of the copper receiving 2 of them, you have 3 of them all total, you now receive all 6 of those electrons. And in doing so, you now end up with 3 copper over here and 2 aluminum over here. So that means up here, you can now, again, balance this out, the 2 aluminum sitting over here, and then over here, that'll give you your, 6 copper on this side. I said 3 coppers on this side, okay? Where's the copper nitrate? All right, okay. This is a 2 there, this is 3 copper over here. So the 2 times 2 give you 6 nitrate, 2 times 2 give you 6 nitrate, 3 copper over here, so I put a 3 here, and now I have my balance equation, and I need to put a 2 over here, okay? The whole process involves this transfer of electrons. So in this case, which one is being oxidized and which one is being reduced? Well, just like our analysis up here, the one that is now losing the electron, the aluminum, is now undergoing the oxidation process, and the copper ion, which gains the electron, is now undergoing the reduction process. Okay? So that means that in this case, the copper +2 ion is now the oxidizing agent. It is causing the aluminum to be oxidized, and the aluminum, of course, is now the reducing agent, causing the copper +2 ion to be reduced in basically gaining electrons. So that is the case where you can actually trace the movement of electrons, and you have metals or metals-non-metal combinations. So that one's actually not too bad. You can actually see the process of charges moving from one place to another. Sometimes it is not quite as obvious. So let's see what else we can kind of see in the other situations where we might actually have just hydrogen and oxygen movement rather than charge movements. Okay. In this case, you can also have a situation where we might have the following. Okay. H2 plus F2, okay, giving you, in this case, 2HF. Okay. So hydrogen gas will combine with fluorine gas to give you hydrogen fluoride gas in this case. Okay? And you go, oh, that's kind of interesting. In the past, we call this a synthesis or a composition reaction, combination reaction. So 2 simple things coming together to form a more complex substance. But we can now actually also see this as a oxidation, reduction, or redox situation. So what are we looking for? Well, look for the movement of hydrogen. Initially, notice over here, I have fluorine by itself. Okay, but when I look at over here, the fluorine now is attached with a hydrogen. Somehow the fluorine gained a hydrogen during this reaction process. So if you look over here, okay, something that gains hydrogen, oh, that's interesting. So if the fluorine gains hydrogen, it looks like the hydrogen is actually migrating, okay, from one side to the other. Let's go a different color again. So again, if you trace the movement of these guys, you can kind of see what's going on. In this case, it looks like hydrogen is actually moving over to this side. So in doing so, when the fluorine gains hydrogen, it is now undergoing reduction. And it looks like, okay, this is now giving up, okay, hydrogen, because now at the end you have one less hydrogen over here, so the H2 is actually giving up any hydrogen. When it loses hydrogen, this is undergoing oxidation, okay? So the fluorine in this case is not acting like the oxidizing agent, basically grabbing the electron, in this case actually the hydrogen, okay, from the H2 molecule right over here. So this can be thought of as an oxidation reduction based on that movement or migration of hydrogen, okay, hydrogen atom. In general, you can also think of this movement of hydrogen and oxygen in the process of combustion, especially hydrocarbon combustion. So for example, if I have a hydrocarbon process where, let's say I have, okay, let's say CH4 for example. Let's take a look at the real easy methane. If you combine with now O2, give you H2O plus CO2, okay? Of course, in this case, this is not balanced yet, but for any hydrocarbon where you have a different subscript for C and H here, this process is still going to be the same. You're still going to have the same two product, just that the coefficients of friends is going to be different, so that you can actually balance them properly. In this case, let's look at what's going on in this situation. If I were to look at this now as an oxidation reduction process, what is being oxidized, what is being reduced? Well, we think in terms of, again, this process, except this time we're going to look at the movement of oxygen. So, for example, if I look at the hydrogen over here, or thinking about the carbon over here, when you see the carbon over here, it was initially connected with the hydrogen. But during the reaction, it now ended up with oxygen, okay, connected to it. So CO2 is sitting right over here. So it looks like somehow carbon is grabbing hold of oxygen, it's gaining oxygen. So when something gains oxygen, this now looks like this is now a oxidation process. So the methane is now being oxidized. It's being oxidized. Whereas in the case of the oxygen, it actually loses oxygen over to the other side. So when it loses the oxygen, this is now being reduced. So the oxygen is now serving as the oxidizing agent. Okay, it is basically oxidizing the other substance in the reaction. Now another way you can think about it is this. Notice that I have the oxygen sitting here by itself to begin with, okay? But when it came to over here, after having lost an oxygen to here, it also gained what? Also gained hydrogen. So in the same way, if I look at what hydrogen is doing, something that gains hydrogen is also being reduced, okay? It tells you the same story. But the oxygen over here is the reducing, okay, reduction process here. It is the oxidizing agent. So either way you look at it, you kind of see, okay, one is being oxidized, the other is being reduced. Whether you trace the movement of hydrogen or trace the movement of oxygen. You can also think about carbon here. Carbon is losing hydrogen, so when it loses hydrogen, again, the conclusion that it is undergoing oxidation process. So all combustion is actually a form of, okay, oxidation reduction, okay, process, okay, in a specific, okay, case. Alrighty. Sometimes you can actually see, okay, some very important considerations. And one thing that we can kind of see is the situation where, okay, you can actually see this process in a demonstration. So let's take a look at a very interesting demonstration that shows us this idea of oxidation reduction going on here. And in doing so, I'm going to have to kind of go from the front there, okay, to show you this. All right. So what I'm going to do is I'm going to go ahead and look at a reaction where I will have, okay, two substances that are going to interact with each other. And they're going to be this over here. So in this particular container, I'm going to go ahead and put some hydrochloric acid. So here I have some hydrochloric acid. I'm going to go ahead and pour some into here. Before I do so, I'm going to make sure, protect myself, so eye protection on. Okay. So I'm going to pour some hydrochloric acid in here. And this is actually pretty strong stuff. Okay. So a bit of hydrochloric acid. And then I'm going to go ahead and look at what happens when I introduce some metals into there. So here I have a variety of different metals. I have some aluminum foil. I also have an aluminum, a 1 yen piece. This is from Japan. I also have a couple of pennies. This is a pre-80 2 pennies. This is actually mostly copper, but 95% copper. And this one is the more modern penny. It's mostly zinc with just a little bit of copper on the outside. So let's see what happens when I actually put these in there. For this one, it's kind of interesting. The more modern penny, what I have done is I've taken a file and kind of filed off part of the edge so that I expose the zinc underneath. So both of the side, I kind of filed it off and rest it. Let's see what happens when I kind of place a little bit of the aluminum foil in there in the first place. So here's some aluminum. Let's go and put the aluminum in the hydrochloric acid and see what happens. Now what you find is that nothing seems to be happening right away. The reason for that is that the aluminum foil actually has a coating of aluminum oxide on the outside. So the acid has to kind of interact with that first before it can actually get into the aluminum metal on the inside. So we kind of give it a little bit of time. And at the same time, let's go ahead and put the aluminum 1 yen piece in there as well. So here's the aluminum 1 yen piece. And let's see what happens there. And then while we're at it, let's go ahead and put the others in there as well. And so here I have the copper penny that is more recent with the zinc core. Put that in there. And finally, the older penny, put that in there as well. So as I sit here and wait, you can already begin to see something a little bit interesting happening. So if you look, you begin to see a little bit of cloudiness. It's going to be hard to see. I'm going to bring it closer to you. Can see it a little bit closer. All right, so I'm going to get behind here. All right. So actually, you can actually begin to see some bubbling occurring. You can see the bubble forming around the newer penny. So all the bubble that is forming right over there. And you can also see now that the yen piece is also showing bubbling effect as well. So seemingly there is now some sort of reaction going on. You can actually see a gas being produced in this process. So both the yen piece and the new penny are showing quite a bit of activity. Lots of bubbling beginning to occur on those two. The aluminum is still kind of floating around, not much is happening to it yet. And then the older penny looks kind of interesting. The older penny is actually getting a little bit brighter. It's not as dark as before, and it seems to be getting brighter, but you can still see a little bit of oxygen, a little bit of bubble forming on that as well. So we're just going to go ahead and let it sit there for a while to see what happens. Over time. I can move things just a little bit. Going back. Okay. Sorry about that. Let me go put it back. And let's take a look at the actual reaction in the form of an equation up here. So let's see what's going on in this situation. So basically what I have here is I have aluminum interacting with hydrochloric acid. So this is the aluminum along with the yen piece, and then here I have HCl, AQ. And let's see what's going to happen in this situation. Now you can actually see a lot of activity going on. Excuse me. And you can actually see a lot of gases being produced. And so we're going to see what kind of gas is being produced in that situation. All right, so in this case, let's take a look at what happens here. Here you're going to have aluminum, solid, plus, here's your H plus ion, plus your Cl minus, and we're going to see what's the process in this situation. So as it turns out, what's going to happen is that there's now going to be a movement of electrons from one place to the other. What you find at the end is if you combine them, the aluminum is going to combine with the chlorine to actually end up with, aluminum, chloride. In this case, of course, stays in aqueous plus hydrogen gas as your product. And that's what the gas is that you're seeing. Gas that is coming off of there is actually pure hydrogen gas that's being produced. So how is that happening? Well, this is happening because if you look very carefully, in order for the hydrogen to become H2 gas, it has to become neutral. So right now it has a +1 charge. It's actually going to be missing an electron. So it has to kind of somehow get an electron from somewhere. But where's it going to get it from? It's going to get it from the aluminum. So the electron actually go ahead and migrates over from the aluminum over to the hydrogen side. So if we look at that, we can now see the following. If I start off with the aluminum over here, and I combine it with the H plus, when it gets to this point, hopefully you're going to end up with Al plus 3. And then of course you have that H2 on that side over there. So that's going to be your neutral process there. Of course, in this case, this is not quite balanced yet, so we need to kind of balance this a little bit. And so if you look at the balancing, each of these would give up 3 of them to that. So that means you need to have 3 over here. But the problem is that you need to have a 2. So that means I need to have probably 6 over here. So put 6 here, and then put a 3 here. That'll give me 6 hydrogen. 6 hydrogen. In that case, where did the 6 electrons come from? They'll come from 2 of your aluminum. So in this case, here's your 6 plus 6 plus, okay, and then the movement of electron goes from there to there. So 6 electrons go off of 2 of the aluminum, 3 each, give you 6 electrons that combine the hydrogen 1 each, give you this 3 H2 here, and then you're left with 2 of the aluminum plus 3 ion, okay? You can really see the activity going now, okay? Now this is really rapidly occurring, basically giving you a whole lot of hydrogen gas on the other side, okay? All right, so in this case, which one is which? What is going on? Well, because the electron is being transferred from the aluminum over to the hydrogen, the aluminum is losing the electron. That means that this is now being oxidized. This is being reduced, okay? So the hydrogen is actually gaining the electron, okay? It is acting as the oxidizing agent in this situation. So quite a interesting reaction, because this is actually how you would generate hydrogen gases, for example. So a lot of times when we actually do experiments where we require hydrogen gases, we use this process to generate a lot of hydrogen gas. And so it's really going quite rigorously. Now, so I'm going to put it on the side so that it doesn't get too dangerous. All right, and we can kind of look at this end result a little bit later on. All right, so that's that particular part over there, okay? Of course, you can actually do the same thing. In place of the aluminum, you can also put the zinc there, and the same thing happens. Okay, the zinc will also be oxidized by the aluminum, by the hydrogen, and the zinc can give off the electron there. So whether you're looking at the zinc within the penny or whether the aluminum from the Japanese yen piece, they both undergo this oxidation reduction process. Okay. Whew. All right, so the next one we're going to take a look at, okay? So the idea is that, okay, why do we say this is a very important process? Because as it turns out, you see that there are a lot of examples in commercial applications where we use a lot of different types of oxidizing agents, okay, to remove electrons from certain situations. For example, in combustion, as you said, any kind of combustion, it doesn't have to be just hydrocarbon combustion. It can be other kinds of combustion as well. Basically, gasoline, hydrocarbon. In the case of gasoline, the oxygen is now the oxidizing agent that will then basically oxidize your gasoline, and the gasoline will be the reducing agent, basically giving up electrons to the oxygen. So that's why in your gas engine, you have to combine the gasoline in a mist form. It combines with air that contains oxygen in order for the combustion process to begin. Without the oxygen, you can't really get that started. There are, of course, things like bleaching agents, for example. So whenever you use bleaches, like Clorox, for example, other things like that, basically what they do is that they actually remove, they act as oxidizing agents, they remove excess electrons from coloring agents that may get stuck onto your clothing, for example. The reason why your clothes will turn dingy and gray or yellowish and so on and so forth is that there are certain color agents that have excess electrons on them. So when you place your clothes into a washer with bleach, the bleach will actually act as the oxidizing agent and grab hold of all those electrons and remove those electrons away from those coloring agents. Once they lose those electrons, they become white. So when they interact with light, it then reflects the whole spectrum of light and not be able to absorb certain colors and give you reflected other colors as well. Batteries, anytime you look at dry cell batteries, they undergo an oxidation reduction process. And that process is actually discussed in the books, and you can actually take a look at that as well. Sometimes something that kind of is cool is things like transition glasses. So glasses where, for example, if you wear these glasses and you go out into the sun, going from the indoor to the outdoor, will actually transition from a clear lens into a darkened lens, almost like a sunglasses, pair of sunglasses. And the reason for that is due to the oxidation reduction. And we'll see that in just a little bit, okay? But those are the processes that you can kind of see. One very important oxidizing agent is actually a very simple one, and it is hydrogen peroxide, H2O2. Okay? And this is a very important oxidizing agent because of the fact that it is used in so many different applications. For example, some of you may actually have hydrogen peroxide in your home, in your medicine cabinet, for example. So one thing you can use it for is as an antiseptic, for example. But usually that particular hydrogen peroxide solution is actually very, very low concentration. So you're looking at maybe about 3% H2O2 in a 97% water solution. So in that case, at very low concentration, you can use it as an antiseptic agent to kind of clean wounds and so on and so forth, minor wounds. But then, of course, you can increase the concentration of the hydrogen peroxide. At about 6% concentration, you can now use it as a bleaching agent in hair salons, for example. When you bleach your hair, for example, you're using a solution of hydrogen peroxide that's about 6% in concentration. By the time you get to industrial and laboratory uses, for example, the concentration of hydrogen peroxide as a oxidizing agent can go up to about 30%. So where would you use something like that? Well, you can actually use it in industrial uses for bleaching flour, for example. Notice when you open up a package of all-purpose flour, it's very white, but as it turns out, the actual original color of that flour is not quite white. It's kind of brownish, yellowish in color. So they use bleach to actually take out those excess electrons to make it nice and white. You can also use it for textile, basically bleaching and whitening cotton fabrics and so on and so forth. Even in tanning, for example, hide and so on and so forth. You can use it to change the color content and so on and so forth. Paper. Anytime you see a piece of paper that's really white like this, because what? The pulp that is used to make this is not white to begin with. So they use a 30% concentration of hydrogen peroxide to make it that white color as well. Now let's kind of take a look at what this does in terms of how hydrogen peroxide can actually be used as an oxidizing agent. So here I kind of show you something that's a little bit interesting. Remember we talked about something important before when we talked about balancing equation. So let's say, for example, if I have H2 plus O2 giving you H2O, for example, we see that we can't just go in there and arbitrarily change the subscript so that we can balance the equation. Because if we do, guess what? We have not just changed water into hydrogen peroxide, and they are not the same thing. To show you that they're not the same, you can kind of do the following demonstration. So here I'm going to go ahead and show you a reaction using water and using hydrogen peroxide and see what the difference is going to be. So in this case, I have water over here, but what I'm going to do is I'm going to go ahead and put a little bit of, this is actually dishwashing liquid. So this is just Joy. The reason for this is just to kind of give it a little bit of, bubbly, so you can actually see anything that might be kind of interesting in there. So kind of add a little bit of that in there. Now I'm going to put some water. So I have about 20 milliliters of water. Rinse that out a little bit. Get as much of the solution there. All right. So now basically I have some soap water in here. So add the rest of the water in here. Stir it around a little bit. So now I have some soap water. What I'm going to do is I'm going to go ahead and add a solution of potassium iodide. So this is Ki, so potassium iodide. And so this has been dissolved in there, at a certain concentration. And let's see what it does when it reacts with the water that's in there. So this is reaction of potassium iodide with water. And there, get it going, and what it does is kind of sit there, mix it a little bit, gets a little bit foamy, but nothing much seems to happen. So seemingly, there's no reaction going on. All this is just a mixture of water with the potassium iodide with some soap in there. So nothing really cool happening in that situation. In the next one, I'm going to do the exact same thing. I'm going to go ahead and pour some liquid detergent in here. So this is again some dishwashing liquid. I think I'm using Joy. Dawn works really well too. I just didn't have any upstairs. So let's put some of that in there. And this time, instead of putting water, I'm going to go ahead and use a 3% solution of hydrogen peroxide. Normally, this particular demo works much, much better if I had the industrial strength 30%, but we don't have any 30% around. We use it all up, so we're going to go ahead and just use that lower concentration and see what happens. And we'll still get the point across. So just push it in there, and put a little bit more, wash more of that. Ooh. Get it in here. So I lost a little bit of it along the way. So let me go ahead and wipe that up. All right. Okay. So in this case, let's go ahead and put this in there. And looks like I lost some of it, so I'm going to go ahead and add just a little bit more into there, just to make sure I have enough in there. That looks pretty good. Okay. That's a little bit more. So now I have some hydrogen peroxide. Roughly the same amount as water that I had before, so about the same, a little bit more perhaps, just because of that uncontrolled spillage over here. All right, so now let's see what happens when I go ahead and add the final ingredient, which is going to be your potassium iodide. In this case, I'm going to go ahead and put this into here and see what happens. Some of you may have actually seen this on the internet or on the Big Bang Theory, for example. They actually had an episode where they actually highlighted this particular reaction. And there's a name for this reaction. It's usually called the elephant's toothpaste. And you kind of see why in just a little bit. Notice right away there is a dramatic color change, that wasn't there with just the water mixing with the potassium iodide. And as it continues to react in there, okay, you notice now there's going to be this kind of foaming that is occurring. So again, because of the fact that the concentration is not that great, the reaction is a little bit on the slower side, so it's not really strong. If I have a much stronger concentration, you can actually see this foam coming over and spilling over and really looking really nasty. Okay? And also at the same time, it's going to be exothermic, so you're going to see some smoke, steam coming out and get quite hot. So my apologies, looks like I might have messed up the proportion just a little bit, but you can kind of see that it is beginning to foam up. So what is that foaming process? Well, as it turns out, that is the production of oxygen gas inside that particular reaction. So let's see what that looks like, okay? And in the process, we are actually looking at, okay, an oxidation reduction process involving the hydrogen peroxide and potassium iodide. So let's see what that looks like. In this case, imagine I start off with the H2O2, okay, in the aqueous form in the solution, and I'm going to add to it, okay, in this case, we have the Ki also in the aqueous state. And so what happens in this case is now the H2O2 still is in the aqueous form, but this now breaks up into potassium and iodide in the aqueous form. So it turns out it is going to be the interaction between the iodide and the hydrogen peroxide that we're going to be interested in. That's what we're looking at. So let's see what happens when those two things get together. So this I'm going to rewrite it down here. H2O2 plus I. I'm not going to worry about the AQ anymore. Just going to go ahead and just look at that situation there. What you find in this case is that this is now going to produce, as it turns out, okay, IO minus plus H2O. It produces a molecule of water, and okay, if you recall, this is now the hypoionic, okay, polyatomic ion. Okay. And so what happened in this case? How did this actually appear? Well, it appeared because of the fact that the H2O2 actually transfer, looks like, an oxygen over to the iodide. So you gotta follow the movement of something. It looks like that an oxygen gets transferred from there to there. So if I look at this, something that gains oxygen is now undergoing oxidation. Something that gives up the oxygen is now undergoing reduction. So what's going on in this case is that, okay, this one is now undergoing oxidation. This is undergoing reduction. In other words, this is now acting as an oxidizing agent. It is basically, okay, oxidizing the iodide ion to form this particular ion. As it turns out, that's not the end of the story. What happens is that once you create this particular polyatomic ion, it can then react with another H2O2 molecule. So let's see what happens in that situation. Let's go ahead and move this up just a little bit now, get rid of that. So now we have the next step of the process where another H2O2, okay, combines now with the IO minus. Okay? And in doing so, something interesting happens. It now creates a single iodide again, plus what you have in this case is now you end up with H2O and an oxygen gas molecule. Okay? You're actually producing now oxygen gas over here. Okay? Producing oxygen gas. And that's where the bubbling is coming from. That's why this is kind of foaming over. That's the bubbling that is driving the reaction. This is the formation of oxygen. But something interesting is happening in this situation. So if we were able to say that, okay, in the first step, okay, the hydrogen peroxide is acting as an oxidizing agent and oxidizes the iodide. Notice what's happening over here. What's going on in this case? As it turns out, what's going on in this case is that the oxygen is actually traveling back over to this side. The oxygen is actually moving in the opposite direction. So the hypoiodide here actually loses the oxygen. So this now becomes reduced in this case, and this becomes oxidized. Interestingly enough, so when you bring this over, you now have H2O3, then two of them comes off as your O2 gas, the other hangs out to give you your water molecule back, okay? So what's going on is the hydrogen peroxide is actually kind of neat. It actually has two phases. It actually acts as a oxidizing agent to begin with, and it oxidizes a single I minus ion, and then it interacts with the IO minus ion, and it acts as a reducing agent and reduces it. Okay, so it gets oxidized in the second step. So depending on the situation, interesting enough, hydrogen peroxide can actually act either as an oxidizing agent or as a reducing agent. The net result, of course, is the fact that you are basically breaking this up into water and oxygen. You're looking at the decomposition of H2O2. So if you were to look at the net equation actually just looks like this. It looks like H2O2 becomes H2O plus O2 gas. And basically the iodide polyatomic ion is actually acting as the intermediary to kind of allow this breakup to occur. And of course, if you want to balance it, you have 2 here and 2 here, and then you have a balance equation. So this is the decomposition process of the hydrogen peroxide. You actually see on this side, you see a lot of bubbling still continuing. So it's a relatively slow process because of the low concentration of the hydrogen peroxide. If I had a 30%, it would have gone really, really fast. So this is a little bit boring, but it kind of gets the point across. All right, so that is another example of oxidation reduction process. Remember we talked about the idea that we can also have oxidation reduction process in transition glasses like this, for example, these lenses here. And as it turns out, there are different ways you can get these transition lenses to occur. One type of transition lenses actually uses silver chloride inside of the glass itself, in the making of the glass itself. And the silver chloride is actually acting as the agent. So the idea is that when the silver chloride is connected together as a compound, when light hits them, it will just basically penetrate right through. There's no interaction. The key is you want to be able to separate the silver and the chloride ion. Once you somehow create a situation where you can take the silver +1 ion and make it into basically atomic silver, so no charge, then the silver atoms can now cluster together to form a cluster that will then absorb light. So when it passes through, it will actually absorb light and allows it to block additional light from coming through the lens itself. And the way you do it is actually through the use of a reaction that relies on ultraviolet radiation. So basically what happens is that when you take this out to the sunlight, when ultraviolet radiation hits it, inside the room here, there's very little radiation that is ultraviolet in nature. When you go outside, ultraviolet radiation from the sun will actually hit it and causes the silver and the chloride to kind of break apart into ions. So that energy is allowing it to kind of separate. Now you would say, well, once it's separated, wouldn't they want to come back together? As it turns out, they're prevented from coming back together because there are actually some copper ions that are scattered throughout the material there as well. And the copper ion, what it does is that it undergoes an oxidation reduction process with the silver, basically giving the silver an electron and allowing the silver not to remain in a atomic state. That does not combine with the chloride ion at this point. And as it does so, it slowly migrates to the top and basically becomes a cluster that would then block light. You can actually see it like this. So if I have, this is actually ultraviolet light, so when I shine on here, you can actually really see very little light. There's some invisible, but in this case, here I have 2 pieces that are exactly the same at this point, they look kind of the same. But notice what happened now when I inundate one of them with the ultraviolet light. So as I let it sit there, the ultraviolet light now is going to go ahead and break apart the silver and the chloride ion, and then the copper will then interact with the silver to give it an electron and make it back into a atomic silver. And those will then cluster together and form a cluster that will then absorb regular visible light. So now when I take this apart, you can actually see there's now a dramatic difference between the 2 lenses. This now has that dark regions in it where it has actually absorbed the ultraviolet radiation and undergone that oxidation reduction process. And if you give it time, then of course what will happen is that without the process of these UV breaking the silver and the copper apart, eventually the copper, the silver and the chloride apart, then eventually they'll come back together to form the chloride. Unfortunately, we don't have all the time, so I'm not going to go over the process. If you're interested, we can actually talk about this during our Zoom meeting as well. All right. The next thing that we want to do is look at the importance of this particular oxidation reduction process in other form. So one that I want to kind of bring to your attention is the following. It's actually a series of 2 reactions that are extremely important to us here on Earth. And so let's see if we can actually recognize what these 2 processes are. So the first one is the following. Let's take a look at this one. Go ahead and look at C6H12O6. Combines with oxygen. I'm going to go ahead and give you a balance equation. We'll then produce carbon dioxide and there's going to be some energy involved. This is actually an exothermic reaction. So when this process occurs, it actually gives off energy to the surrounding. Okay? So when you look at this, you say, well, what's going on in this case? We recognize this as oxygen gas, but what is this over here? Somebody may actually recognize that. Okay? That is actually just a what? Okay, a glucose molecule. So it's a sugar molecule. And in this case, okay, this process is nothing more than a process that, okay, drives metabolism. That allows us to basically obtain energy, okay, for our everyday functions, for example. So as we burn this fuel, so to speak, okay, through this combustion process, we produce carbon dioxide, okay, and water, and then of course the energy that we need to do work. So how is this an oxidation reduction? So what is being oxidized and what is being reduced? Let's see if we can kind of figure that out. So again, if you look at the situation, going from here, here's your sugar that has carbon, hydrogen, and oxygen. When you see something similar on the other side, you see this, and carbon and oxygen is now missing the what? Missing the hydrogen. It doesn't have hydrogen anymore. So if you recall, when you talk about hydrogen, if something loses hydrogen, it is now undergoing oxidation. So what you find is that in this case, okay, this part right over here is undergoing the oxidation process. Okay? So if that's the oxidation, what happens over here? Well, the oxygen sits over here, and when you see it again over here, it has now gained the hydrogen that was lost by the sugar. So in this case, gaining the hydrogen, this is now being reduced. So this is the reduction part of the reaction. This is now the oxidation part of the reaction. Okay? So that means that this is now the oxidizing agent. So as it turns out, the reason why sometimes we see the word oxygen in oxidizing or oxidation reduction is because of the fact that the oxygen is a readily available oxidizing agent. It does a lot of oxidizing work, so to speak. Whether it combines with sugars to produce this process, or whether it combines with metals, for example, to produce metal oxides and so on and so forth. Okay? In the same column on the periodic table, you also have sulfur. So sulfur also acts as an oxidizing agent quite often as well, producing the ores of the different metals that we see around us. So this is the oxidation reduction process that's going on over here. Okay. Interesting enough, when you get to this side over here, what you end up with, the carbon dioxide and the water, these are called oxidized forms of matter. Okay. They are the result of oxidation occurring from something. And as it turns out, anytime you have oxidized forms of matter, they are very low in energy. Okay? So they're low in energy. They don't contain a whole lot of energy that we can actually extract, so to speak. Okay? And this is really the byproduct. The reason for that, of course, most of the energy actually came up over here. Okay? It's now being utilized by the surrounding. So this is actually the core of metabolism. Okay? When biological entities require energy, they would then use stored sugar and use oxygen to produce this oxidized form of matter with energy that can now use for work. Okay. Interesting enough, I could just take this same equation but rearrange it just a little bit. I could actually now take carbon dioxide and, in this case, water, in the same ratio, 6 to 6, and I can now reverse the process. When I do so, I end up with C6H12O6 plus O2. Okay? So you say, wait a minute, isn't this the exact same reaction? So what's the big deal? Okay? Well, in this case, let's take a look at what's going on. In this case, what's going on in terms of oxidation and reduction? Well, let's take a look. In this case, if I look at the CO2 over here, the carbon dioxide, when it went from here to the end product, it actually, again, gained hydrogen. It gained hydrogen. So when it gained hydrogen, what happened? Well, this is now basically undergoing reduction. So the carbon dioxide undergoes reduction, and it is basically being reduced by the water over here. So the water is actually undergoing oxidation. And again, you can see that from going from here to over here, going from H2O to O2, you basically lost the hydrogen. You lost the hydrogen. When you lose the hydrogen, you're undergoing oxidation. So interesting enough, when this occurs, the carbon dioxide is now acting as the oxidizing agent, oxidizing water. And in order for this to happen, however, you must put in energy. So whereas before this was an exothermic reaction, this is now an endothermic reaction. energy has to be put in order for this process to occur and to produce this as the product. Okay? And when you produce that as a product, this thing over here, where this is given the name of oxidized form of matter, this is now a reduced form of matter. As it turns out, reduced form of matter will have high energy content. This is where you actually store up energy. Okay? You store up energy in these types of matter, whether it's going to be in complex sugars, even in things like gasoline, for example, coal that we dig up from the ground, and we can actually undergo this process. Okay? All these things, these reduced forms of matter will be high in energy content, and we can then reverse the process to extract the energy back out through another oxidation reduction process. Okay? Some of you recognize this. This is actually nothing more than what? Photosynthesis. So in plant, for example, plants will make use of sunlight, energy from sunlight, to convert carbon dioxide along with water to stored sugar and oxygen, released to the environment. So these two are complementary processes. That is just a reversible type of process, one from the other. All right, so that kind of wraps things up. And again, if you look at the two lenses now, they're pretty much almost the same again, because without the addition of ultraviolet radiation, the process of oxidation reduction doesn't get maintained and it reverts back to the original state. Okay. And again, as I said, if you're interested in this, you can actually contact me individually on Zoom, or we can actually talk about that a little bit more as well. Okay. All right, so this kind of wraps up some of the things that I wanted to talk about in terms of oxidation reduction. There's a lot more that we can talk about basically, but unfortunately we're kind of running out of time, so we have to kind of pick and choose our battles, so to speak. So make sure that you go ahead and continue working on the homework assignment from chapter 9, and then until the next time we see ourselves on Zoom, take care, and I'll see you next time.